In theorem 15.1, we develop a test for conservative vector fields in the plane. Let M and N have continuous first partial derivatives on an open disk R. The vector field f of x comma y, which is going to be equal to mi plus nj, will be conservative if and only if the partial of n with respect to x is equal to the partial of m with respect to y. So you're taking the partial of the component function for I with respect to y, and the component function of j with respect to x. And if those two partial derivatives are equal to each other, then the vector field given by f will be conservative. Let's take a look at example 5. They want us to determine whether the vector field is given by each of the conditions is conservative or not. Let's go ahead and work through this. So if we do example A to start, the m in this case is x squared y. The n is equal to x y. And here's what we need to check. We need the partial of n with respect to x. If I take the derivative of this function, the partial derivative of this with respect to x, we're going to get y. If we look at the partial of m with respect to y, the partial derivative of this function with respect to y would be x squared. We see that those two expressions are not equal to each other. So partial m with respect to y and partial m with respect to y are not equal to each other. So this one would not be conservative. So A is not conservative. Let's do part B now. If we look at the vector valued function given by f in part B, we see that m is equal to 2x, n would be equal to y. So if we check for conservation, let's go ahead and do that. We're going to take the partial of m with respect to y. Well, with respect to y, the derivative of 2x would be 0. If we look at the partial of n with respect to x, the derivative of y would be 0. And so we do see that in this case, the partial of m with respect to y is equal to the partial of n with respect to x. And so this vector field would be conservative. So f is conservative. This is a pretty convenient and easy check for us when we have the expression to see whether or not the vector field is conservative. Let's take a look at example 6. In example 6, we're asked to find a potential function for f of x comma y. So recall, a potential function for f of x comma y is going to be a function, little f, such that the gradient of little f would be equal to capital F. One of the things we'll do up front is let's just check and take a look at this function to see whether or not it would actually be conservative or not. So here, if I wanted to calculate the partial of n with respect to x, that would give us 2x. If I calculate the partial of m with respect to y, the partial of 2xy with respect to y is going to be 2x. So this vector function f, this vector field, will be conservative. Now our goal is to find a potential function. So we want to find little f of x comma y such that del f of x comma y, the gradient, is going to be equal to capital F of x comma y. So let's think about this for a minute. So what is del f of x comma y? Well, that's the partial of little f with respect to xi plus the partial of f with respect to y j. We want this to be equal to f, which is equal to 2xyi plus x squared minus yj. This statement here is the equality of two vector valued functions. For this to occur, we need the component functions to be equal to each other, meaning we need fx, in other words, we need the partial of f with respect to x to be equal to 2x yi, and we need the partial of f with respect to y to be equal to x squared minus y. And then the thing that's nice, we've seen things like this, it's like a anti-differentiation problem. So if we wanted to solve, let me revert back to the old notation, the Leibniz notation for the partials. The partial of f with respect to x, this is equal to, I didn't mean to write that I on there, just the components. This is equal to 2xy. So if we want to recover f, we want to remove this partial derivative. So we want to integrate both sides with respect to x. So I'm going to take the antiderivative of the partial of f, partial of x with respect to x, and I'm also going to do that to the right-hand side. We want to integrate this right-hand side with respect to x. If we do that, we get that f of x comma y will be equal to, let me move up so everybody can see, f of x comma y is going to be equal to the antiderivative of this function with respect to x. We hold y constant, should give us x squared y plus, remember, whenever you integrate with respect to x, we treat g as a constant, so we could get some function of y as our constant of integration. Similarly, we want the partial of this function f with respect to y to be equal to x squared minus y. So we're going to go ahead and integrate both sides with respect to y. The antiderivative of partial f, partial y, dy is equal to the antiderivative of x squared minus y dy. This will tell us that the partial of the f of xy will be equal to x squared y minus 1/2 y squared, and whenever we integrate with respect to y, we could get a function of x here. Let me call that h of x. So we have two expressions for f, and we would like for them to be equivalent. If we kind of compare the two, they both have the x squared y term. Here we have a function of y, and we have a function of y in this expression. So if we kind of just set those two equal, what we get is the following. We have f of x comma y equals x squared y minus 1/2 y squared, and then h of x, this is a function of x here, this part's missing, so that's just kind of a constant. And I claim that this is going to be our potential function. We can check this. So if the gradient of little f is equal to capital F, then we have found our answer. You don't have to check if you don't want to, but this is the first one we've done like this together, so let's go ahead and do it. So check, is it true that the gradient of f, does that really equal to capital F? Well, the gradient of f of x comma y the partial, whoops, if I can get rid of this. If I take the partial of this function with respect to x, that's going to give us 2xy. That'll be multiplying to I. And then plus, now we need a partial with respect to y. The partial with respect to y is going to be x squared minus y. And that will be j. And if we check from above, that is indeed equal to the vector field f of x comma y. So we found our potential function simply by a matter of, doing some antiderivatives of the component functions.